Hello and welcome back to week 2 of EC 497, Introduction to Human-Robot Interaction. I'm your professor, Dr. Carlotta A. And this week we are going to talk about classifying human-robot interaction. The objectives for today's lecture are to state the categories for human-robot interaction, for classification, describe the different roles of interaction between the human and the robot, list human-robot team compositions, describe the task, time, space, and taxonomy, define situational awareness in human-robot interaction, and list HRI design guidelines based upon improving situational awareness in HRI. Although a lot of this will seem to be centered around mobile robots, the design guidelines as well as the taxonomy can also be applicable to a stationary robot such as our Blossom robot. Remember, your ultimate goal is going to be to then use HRI design guidelines to make an interaction scenario between a human and your robot that you're going to then evaluate for your final project. So the first question is, why do we need to classify? It is a great way to measure the properties of a human-robot interaction or interaction design, and this is important because it gives you a way to compare systems about regard to things that are going well, things that are not going too well, what's working, what's not working. And the categories could be several things, but for this lecture, we're going to focus on the autonomy level of the robot, as well as the team composition, such as how many humans, how many robots, a presentation of the type of sensor data and how you could use that, as well as how do you specify a task or mission for the robot to complete. So some examples of the taxonomy for the roles of the human is one could be commander, which means the human's point of view is God's eye or remote spatial relationship. This could be an example of NASA engineers here on Earth who are looking at the Mars rover, looking for soil or water remotely. Another example would be peer, or the human's point of view is now bystander, where the spatial relationship is there beside the robot, such as a robot working next to a human on a manufacturing line as a cobot, but they may have no actual interaction. They're just beside each other. Another role could be teleoperator, where the human's point of view is from robot's eye, and it could be robot immersion, such as a human using a teach pendant in order to program an industrial manipulator to complete some task. The last role could be developer. From a human's point of view, it would be homo nucleus inside of the robot, where this could be the engineer, the developer who actually created the operating system for the robot. So another way to think about the roles of interaction is in terms of supervisor, operator, teammate, mechanic, programmer, and bystander. So a supervisor would oversee a number of robots, and it needs to have a global picture of the robots and the mission and understand when a robot is having problems that may affect the mission. In this case, where one member of the team may be supervising multiple robots that are playing RoboCup soccer. Another example would be an operator, such in this case, where a doctor may be using a Da Vinci surgery system. So the doctor needs to have a telepresence to understand where the robot is and what must be done. And the interactions between the human and the robot may depend on level of autonomy, where some things the doctor lets the robot do on its own, and sometimes for high-level tasks, the doctor may step in and do teleoperation. So the robot has to be able to be operated on both levels, and there needs to be an awareness of the environment, robot, task, and mission by the human. A teammate, such as in this military operation, the soldier may see the robot as a member of the team, where the teammate can now give commands within the scope of the mission or the task. However, the human must understand the limitations of the robot to make sure it's not asking the robot to do something where it may not have the sensors or the hardware or the capabilities in order to execute that command. A mechanic or a programmer now would have to also understand the internal workings of the robot, because they may have to step in order to fix the hardware or the software on the robot. So they have to be able to have the capability to interact from the outside in order to identify, troubleshoot, and solve a problem. And finally, the bystander may have no formal training or understanding of how the robot works, but it must be able to coexist with the robot. This could be an example of a human stepping in when you have a food delivery robot to get it untangled from a curb cut or get it untangled from another robot, or maybe even just to go around it in order to help it to finish its mission or task. So in these roles, one user may assume a number of roles for a particular robot, or a number of people may interact with one robot in different roles. And sometimes you may even have to design an interface to support a given role to make it easier for the human to be able to watch, guide, or command the mission. So autonomy measures the percentage of time that a robot carries out a task independently. And this could be a single value if the autonomy is at a fixed level, or it could go from anything from 0% for teleoperation to 100% for fully autonomy. Or if it's shared autonomy between the human and the robot, there may be some mixed autonomy that is along some level or range, where when an intervention is created by the human, the intervention may make the two sum to 100. So here's an example of the first movement of Robonaut, where it's just walking through the sequence to start up. So this is fully autonomous, whereas if it gets stuck, the human may be able to step in at some point.
Okay, we have power on this time.
And Mike, we're back with you on 2. Just wanted to give you a heads up that we can see you through Robonaut's eyes.
And we have his arms stretched out. He's kind of like the patient in physical therapy has been in a cast. We need to start going through range of motion.
So in that case, the operator did not just stand in, but was just a bystander to make sure that the robot was able to execute the mission. So there's also shared autonomy, where you measure the percentages, as we said, of where you want the robot to fully complete the mission or task and where the human has to step in. So here's an example of a discussion of shared autonomy.
So what does shared autonomy actually look like? Well, robots perform difficult tasks, like seeing to bridges, metro systems, oil and gas platforms, and smart factories, and even space to perform dangerous tasks.
Because of the scale of these assets, it's impossible for humans to do that effectively and efficiently. This is where robots come in. Now, in classical robotics, we had a very clear separation between the workspace of robots and where humans would operate. Now, that workspace is becoming blended, and that brings new challenges.
One of the exciting things about robotics from a business perspective is that they don't tire, they don't go on holiday, they don't call in sick, so you're actually saving a lot of money. But the same story also has to be seen from the employee's perspective, because if you all of a sudden have somebody that does your job twice as good in half the time, you might actually have a problem.
In the next 10 years, University of Oxford estimates that 80% of jobs in America are going to be partly or fully automated.
We're not just talking about blue collar, but also white collar jobs. What are we going to do with those people who no longer can do the job that they're used to do? The ideal outcome would actually be to have robotics and humans work in tandem in the sense of shared autonomy.
This new paradigm is about equipping people with new tools. Humans are very good at cognitive decision making. We are very good at contextualizing. Robots are very good at repeated, powerful actions. So marry the best of both worlds, human decision making and the precision, power, and accuracy of robotics.
Even there, we can see a risk that has to do with de-skilling. Yes, it is fantastic that you have self-driving car taking over decision-making, but at the same time, you might de-learn how to drive properly. The issue of de-skilling always emerges whenever you use any type of technology. How many cell phone numbers do you know by heart? How much do you rely on spell correction? How do you navigate through the streets? Of course you rely.
So we've talked about a little bit about the shared autonomy and the different types of human-robot ratios. It could be one person, one robot, one person, many robots, many people, one robot, many people, many robots. Obviously, based upon the team composition, you may have to think about levels of autonomy as well as situational awareness, such as many people on one robot. Are you and the other people on the team giving the robot conflicting information, or one person on many robots? Is the person actually aware of what all the robots on the team are doing? So here are other ways to look at these compositions where you have a one-to-one relationship, or one human controlling a robot team where the robots are working together, or one human controlling multiple robots that are not working together, or multiple humans working together on one robot, or two individual humans trying to control the same robot, and so on. So all of these different ways require different levels of autonomy for the robot and awareness for the humans. So here are some examples of a homogeneous and heterogeneous team where all robot members are the same and complete some mission or task. Or if you have a heterogeneous team, you now have to be aware of which robot has gears, which one has wheels, which one has omnidirectional, which one has tracks, which one has an arm, which one has a camera, so that you can make sure that you are commanding the appropriate robot based upon the sensors that it has and what it should do next. So criticality is based upon measuring the potential for harming humans or environment in a particular domain given a failure. For example, if you have a bomb disposal or IED disposal robot, and then the robot making a mistake such as falsely identifying where there was no bomb, that could be very, very dangerous, and a high failure, which could be very dangerous to humans. Whereas if you have a robot that's vacuuming your floor and it misses a spot, that's probably pretty low criticality to the human, or somewhere in between, such as in a manufacturing facility. It may be medium level, depending upon where the robot is and the proximity of the humans to it. So other levels of the taxonomy include time, such as whether the robot and the human are working in a synchronous mission or task, such as on the left, where the robot has to feed the person, or on the right, where we now know that the robot may be in space and the operator and robot may be in different times as well as locations. Another example, once again, is space, which we've talked about before, where now the robot and the human may be co-located, working in the manufacturing facility together, as seen here with this Baxter robot, or non-co-located, where they may be functioning in different spaces, where the robot is now being controlled remotely. And a term that has been brought up a lot, especially when you are remotely controlling a robot, is situational awareness, where situational awareness is now tied to the robot has to perceive what's going on in the robot's, and the person has to perceive what's going on in the robot's environment, comprehend what's happening, and predict what's going to happen next. So here's the environment. The operator has to understand the situation, including internal and external goals for the robot and the robot's knowledge. Then it has to supervise the skills and behavior selection that the robot is choosing to do in order to complete some mission or task. Then the robot executes that action in the midst of what may be disturbances such as low battery, power failure, a human in the space, getting lost, getting stuck, sensor failure, etc. Then the robot interacts with the environment with the sensors in order to have some perception of the environment in order to get that situation that the human, once again, has to be aware of. So situational awareness is basically the knowledge of what is going on around the human operator and or the robot in the context of a mission or task to be completed. So situational awareness in urban search and rescue, for example, would be looking at things such as, did the robot get lost? Is it keeping track of where it has been or where it has to go next? Is the robot disoriented? Does the robot have good vision? Can it see? Are the camera or other sensors occluded or blocked? Are there limited sensor modalities for what the robot has to do in order to achieve the mission? And robot safety and robot health. Is the robot going to get stuck, in this case, inside and not be able to navigate out from some kind of failure? And here's another framework based upon, once again, directing that team for robot soccer, where now you have to give one human, one robot. HRI awareness is the understanding that the human has of its location, activity, status, and environment. And the robot has to have an understanding of the human's commands necessary to direct its activities, and constraints must always be under which it must operate. For example, if the human tells the robot to go and pick up a Pepsi can, does the robot know what a Pepsi can is? Does the robot actually have a gripper or arm in order to do that? Can it actually complete that mission? So here's a framework where now the multiple humans and robots have to interact together, and there has to be awareness of the human to the robot to the human, the humans who may be on the team directing the robot team, as well as what all the robots are doing. And the human has to also evaluate the overall mission and whether it's being achieved. So the robots have to know where the other robots are. Was the kick successful or not? The robot has to self-evaluate that. Where did the ball go? Where are the robots on its own team, on the opposing teams? And did one robot just have a failure and can no longer be used in the task or the mission? And are the robots moving into a different position that the robot now has to be aware of? For example, where's the goal? And then did a robot on the opposing team also fail? So all of these are things that the human has to evaluate whether the mission has been achieved or not, but the robots also have to have some awareness of that. So HRI awareness, once again, human to robot. Human has to understand location, activity, status, and surroundings of the robot, and also the certainty of which humans know this information. Humans have to understand the location, identities, and activities of their fellow human collaborators. Who's driving which robot? How are the robots coming together, etc. HRI awareness can also be robot to human, where the robot's knowledge of the human's commands need to be to direct activities. And what are the human constraints that may require command non-compliance or a modified course of action? For example, if the human asks the robot to do something it just cannot do. And then robot to robot, the knowledge of how many robots are on the team, what commands have each robot been given, and robot to robot coordination, such that if one robot has a failure, how to immediately dynamically reallocate that task among other robots so that it can still be achieved. So human understanding of the overall goals of the joint human-robot activities and the measurement of moment-by-moment progress as obtained. So here's a video of robot-to-robot communication where they have to achieve a task where only certain robots are able to communicate with others because they have an awareness of the situation that some of the robots do not.
A recent trend in robotics is to get lots of robots working together. But parallel operation is not always enough. Some tasks are just too difficult for the robots to solve on their own. So-called self-assembling robots can combine forces by connecting to each other in a broad range of morphologies. But it's hard for the robots to know when to use different morphologies because of their limited local sensing range. The solution? Flying robots. Flying robots can analyse the environment to see what task needs to be solved, what morphology is most appropriate to solve that task, and which robots are best placed to form the morphology. However, it is non-trivial for the flying robot to communicate with specific robots on the ground. The problem is that the robots have very different views of the world, which makes it difficult for them to agree on a common frame of reference. We have developed a method that allows robots to select their communication partners without relying on any kind of global coordinate system. We refer to our method as spatially targeted communication. Let's say a flying robot wants to communicate with a specific robot on the ground, this one, for instance. To start the selection process, the flying robot illuminates its red LEDs. To join the selection process, the robots on the ground light up in blue. In a series of elimination steps, each ground-based robot independently displays a sequence of randomly selected colours. At each step, the flying robot matches the colour of the target robot. Whenever a robot on the ground sees that its own colour doesn't match the flying robot's colour, it eliminates itself. The process continues until only the targeted robot is left. An extended version of this method allows adjacent groups of robots to be selected and then given movement and morphology formation instructions. Here, the flying robot has already targeted the 4 robots closest to the hill and instructed them to form a line morphology. Spatially targeted communication expands the potential of self-assembling systems by allowing ground-based robots to benefit from cooperation with flying robots.
So in conclusion, the HRI design guidelines are to enhance awareness by providing a map of where the robot has been, where the robot is going, or provide more spatial information about the robot in the environment. It's also to provide a lower cognitive load for the human by providing fused sensor information or displaying important information near or fused with the video image or other sensor data in order to make it easier for the human to understand the current status of the robot as it completes the mission. And also to increase efficiency, such as by providing user interfaces that support multiple robots in a single window, or minimize the use of multiple windows and maximize the use of a primary viewing area for the human to make it easier to understand what's going on or the status of the mission, and also to provide help in choosing robot modality, such as giving the operator assistance in determining the most appropriate level of robot autonomy at any given time. And this concludes week 2 lecture. Have a great day.